Hey guys, Dave Cummings here from PLNU. I want to talk to you about how vaccines work. If we want to understand COVID vaccines in particular, we first have to understand the basics of how all vaccines work. And so this video is really about vaccines in general, and the following video will be about the specifics of the different COVID vaccines that are in use today. And today is May 11th, 2021. So specifically, I want to show you a little historical impact of vaccines, and I want to briefly touch on rumors that have been in circulation since the late 1990s about vaccines causing autism, and in particular the MMR vaccine being associated with autism. Then we're going to look at the goal of vaccines. The goal of vaccination is to build what's called immunological memory, and I want you to understand at a cellular level what immunological memory actually is. And then I'll show you just how effective immunological memory is by looking at antibody titers, we call them, the concentration of antibodies in the bloodstream, in what is a primary response and a secondary response. So primary being in response to the vaccine or the first exposure to the live pathogen, and the secondary response being exposure again, or in the case of a vaccine, for the first time being exposed to the live pathogen. So let's talk a little bit about the history of vaccines in our country and some of the impact that it's had over the course of the last 100 years or so. So what you see in the left column here are various diseases that are vaccine preventable. Then the first column beyond that is baseline 20th century annual morbidity. In other words, back in the 1900s, pre-vaccine for that particular infection, 1900s pre-vaccine, what was the annual rate of illness? That's what morbidity refers to. And then the next row is the 1998 annual rate of morbidity or illness as the average from 1990 through 1998, and then a percent decrease. So if you look at smallpox to begin with, you see that early 1900s, smallpox was causing about 48,000 infections per year in the United States. And between 1990 and 1998, the average was 0 per year. It is completely eradicated from the United States. Diphtheria, early 1900s, was at about 176,000 cases a year. In the 1990s, it averaged 1 case per year in the U.S. Pertussis at 147,000 cases per year pre-vaccine, a little over 6,000 cases per year in the 1990s. Tetanus went from about 1,300 cases down to an average of 34 per year. Polio went from 16,000 down to 0 per year, eradicated. Measles, over 500,000 cases per year in the 20th century, and since that MMR vaccine, we're averaging about 89 cases per year in the 1990s. Mumps, 152,000 down to 606. And if you jump down to Haemophilus influenzae type B, that's the Hib vaccine. Early 20th century is about 20,000 cases per year, and 1990s were in the 50s, averaged in the 50s of cases per year. And you can dig up these data and read all about it on your own if you like from the Morbidity and Mortality Weekly Report, the particular issue down at the bottom of the screen. So what you can see here is that vaccines have made a huge impact, a huge impact. So even though our population size is growing dramatically, the frequency of these illnesses in the United States has dropped dramatically post-introduction to vaccines. Here's a couple graphs that show two of these. This is polio. And what you can see starting in around 1950 up until about the present time, the first polio vaccine was introduced by Jonas Salk in 1955. That's the first arrow. And you can see a dramatic drop from the time that first polio vaccine came around to the time the second vaccine came around, the Sabin vaccine 6 years later, which was an oral vaccine, and that's because it's so much easier to distribute. The oral vaccine has made its way around the world. But you can see that even by the time 6 years later the oral vaccine came around, polio was on the run because of the first vaccine. So the introduction of these two vaccines in the 1950s and early 1960s have essentially wiped out polio. And the next graph, this is measles. So you can see mid-1960s when the measles vaccine, what we now think of as the MMR vaccine, was introduced. A couple years later, the numbers dropped off. They continued to drop as vaccination rates went up, and we're at essentially 0 cases per year, except in small pockets where people either can't get vaccinated because their bodies won't tolerate it, or they've chosen not to be vaccinated for various other reasons. So what you can see in these graphs is over a very short period of time the impact that vaccines can have on our overall public health. Now, you may have heard a connection between the MMR, measles, mumps, rubella vaccine. You may have heard a connection between that and autism. That came from a report in a very reputable journal, The Lancet, in 1998, authored by Andrew Wakefield. It turned out, unfortunately, that Wakefield had fudged the results. He was being paid, it finally came out, by lawyers of parents who were in the midst of trying to sue the vaccine makers, and they needed more data to be able to effectively sue them for their children's health conditions. And so he came up with the data for them to support their lawsuit. Sadly, he lost his medical license over this, and the journal, with its tail between its legs, retracted the article. Unfortunately, the rumors continue to circulate, right? The announcement that there was this supposed connection between autism and vaccines hit every news outlet and spread like wildfire, and the announcement that it was retracted and Wakefield lost his medical license over fudging the data, unfortunately, did not make such big news. But you can look this article up on your own. It's still available, and when you pull it up, it has that big red word retracted across every single page. This is not something I typed on top of it. That's just a screenshot straight from the journal, straight from the source. But this was the first article, and really the only one with any solid evidence, that made a connection between autism and vaccines, particularly the MMR vaccine. And virtually every health agency around the world today agrees that there's just no data to support a connection there, and we need to look elsewhere for an understanding, for an explanation of autism, a very serious issue, but MMR does not seem to be behind it. So, to understand why we vaccinate, you need to understand immunological memory. This is the goal of all vaccinations. This is a natural process that our bodies already do, and the idea of a vaccine is to get our bodies to do it without us having to get sick in the process. So let's say that a virus shows up, and that's represented by our little hexagon. Viruses are essentially hexagonal. When they enter our bodies, they're going to activate the 2 branches of our adaptive immune system. The cell-mediated branch, which is driven by what we call T cells, and the antibody-mediated branch, which is driven by B cells. Now, there are millions or billions of each of these T cells and B cells in our bodies, and each one has a slightly different receptor for the pathogen that they might see. So for the T cells to find, for the appropriate T cell with the perfect receptor to bind to the surface of a given pathogen is like finding a needle in a haystack. But eventually, the system does tend to work, and the needle is found in the haystack. And when that 1 or 2 T cells and those 1 or 2 B cells that have receptors that match perfectly to some antigen on the surface of our pathogen, when they do finally bump into the pathogen, what they do is clone themselves. Because at first they were 1 in a million. Now they're no longer 1 in a million. Now they're the majority. So they clone themselves, so they make millions of copies of themselves with the exact same receptor on the original parent cell, original parent T cell or B cell, so that they're no longer a needle in a haystack. So that's the first step, and we call that clonal expansion. What do each of these populations do? Well, the T cells go out and circulate through the human body looking for human cells that have viruses hiding inside them, because viruses replicate inside our cells, which makes it tough for other parts of the immune system to find them. So what the T cells do is they search for cells that have the virus hiding inside, and then they kill those cells. They break them apart. It's called lysing. They lyse the cell open, and now all the viruses are exposed to the rest of the immune system, like the B cells. So what do the B cells do? The B cells don't go searching for cells that are infected. Instead, the B cells secrete antibodies. We talk a lot about antibodies. This is where they come from, the B cells. Antibodies are shaped like a little letter Y or a peace sign, and they have receptors on the end that match the receptors on the same B cell that produced them and that found this pathogen in the first place. And these antibodies just perfuse the whole body, looking essentially, from a molecular perspective, for the pathogen. And wherever they find it, they stick to the surface of the pathogen, like you see the antibodies coating the surface of our little virus here up at the top. So what's the purpose of that? Well, antibodies do several different things, but the two most important things are what we call opsonization and neutralization. Opsonization is when these antibodies have coated the surface of the pathogen. It turns out that it makes it easier for our phagocytic white blood cells to find the pathogen, attach to the pathogen, engulf it, and destroy it. And that's the key, right? That's ultimately the goal of this adaptive immune response, is to find and destroy the foreign objects that don't belong. When the foreign object is not opsonized by these antibodies, macrophages have a little tougher time finding them, and the process is much slower. If we coat them in antibodies, the process speeds up and is way more effective and way more efficient. We call this opsonization. Now, neutralization has a similar function in that the antibodies coat the surface of the pathogen. For the pathogen to infect the next human cell, it has to actually attach to that human cell first. And the antibodies actually block its ability to attach. And so what happens is it bounces right off. Like that? My cool little high-tech animation. It bounces right off rather than attaching to the surface. And so we can neutralize the pathogen. In other words, the ones that are in circulation that haven't yet been consumed by phagocytic white blood cells don't pose any more threat to infect the next host human cell because they're opsonized and neutralized. Make sense? Okay, so opsonization, neutralization, both carried out by antibodies, which are produced by B cells as part of this whole response. Now, we said that the T cells clone themselves, the B cells clone themselves, and these two populations of cells fight this primary infection until it's gone. Usually they linger for weeks to make sure that they've really gotten this thing. But at the same time, there's a population of both T cells and B cells, clonal, so they're carrying the same receptor and therefore the same sensitivity for this little pathogen right up here, the exact guy that activated them in the first place. But these are not going to fight in the primary infection. They're actually going to hold back as what we call memory cells. Memory cells don't get involved in the primary infection. They wait for a secondary exposure, weeks or months down the road. Why is that important? Well, it turns out that the T cells and the B cells that are active in fighting have a relatively short lifespan, right? Weeks to months at the most, and they die off. These memory cells, under perfect conditions, will last your whole life. Realistically, some pathogens induce longer-lived memory than others. And the whole goal of designing a vaccine in the first place is to create one that stimulates the strongest memory response, the biggest T cell and B cell memory populations around, that have the longest lifespan, that don't peter out too quickly, and potentially even stick around your entire life. Okay, so for example, you don't get boosters of the polio vaccine. One shot of the polio vaccine and you've got lifelong immunological memory. Now, why is that not true with other vaccines? That's complicated. It's a story for another day. But some exposures, either to the vaccine or to the live pathogen, result in lifelong memory. Others, the memory is shorter, lots of pieces involved. But these memory populations of T cells and B cells, and then continued circulation of those antibodies, is really the whole goal of vaccination. And being able to do that without being exposed to the live pathogen and having to experience illness in the first place. What does that look like? This graph here shows the concentration of one of our antibodies in our bloodstream after first exposure to a pathogen. That could either be the live pathogen and you got sick, or to a vaccine. And then later, shows 2 months later, secondary exposure to the same pathogen again. What you see is that, and if you notice and this is just time on the x-axis. On the y-axis, it's a log scale. So we go from 1 unit per whatever, 1 concentration unit of antibodies, to 10 to 100. So it's going up in tenfold steps. You can see that it takes a good 3 days for our antibody count after our primary exposure to begin climbing, and then slowly over the coming months, it goes down, 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 down. But the memory T cells and B cells are available to be reactivated, and boy, do they reactivate fast. Look at this. Way, way faster than our original primary response, and 100 times more concentrated antibodies being produced. So the overall response is more intense and faster. In fact, it's so intense and so fast that chances are the pathogen doesn't even give you personally a conscious hint that you've been infected. You never feel any of the signs or symptoms of disease because your memory response pounces on it so fast. And that's really what we're after. We're trying to get to this point here so that if the first exposure is the vaccine, then we hopefully don't get sick, but we do sometimes. The second exposure is when we see the real pathogen and we never even know we saw it, because that memory population of T cells and B cells and circulating antibodies clears the pathogen before it ever starts an infection in our bodies. All right, let's summarize some of the key take-home points. Morbidity, sickness of many infectious diseases has dropped dramatically since the introduction of vaccines. That's undeniable from the data. The report implicating MMR vaccine and autism was retracted, and Andrew Wakefield was barred from practicing medicine for fabricating the data. Important to know. And memory T cells and B cells respond very quickly to a secondary exposure, clearing the pathogen before infection can set in. All right, feel free to watch this video a couple times if you need to. Pause it as often as you need to, and make sure all of this makes sense before you go on to the next video looking at the actual vaccines used for COVID-19. Thanks.